Okay, so for our second lab, we're going to do reflection, refraction. That is another name, low refraction, which is called Snell's law. So go to Canvas, go to modules, and then click on refraction, Snell's law, and you should get. And I'm going to show another file, and this is what you're going to get. Okay, so the objective this experiment is that we want to study Snell's law and to determine the index of refraction of a D lens. So let's find out what is the law of low refraction, which is also called Snell's law. So this is a diagram. So we have, let's say you have two different material. So this material has an index of refraction, which we call the N1, and the second material we call that we have the index of refraction, which we call that N2. And you have the normal line here. So when you have a light that's striking at the at the surface, or what we call the interface, what's going to happen is that you have the incident ray, you have the reflected ray. In addition to that, you have the light ray that's coming into the second material, and this light ray is called the refracted ray. So the angle associated with that is called the theta r. This is theta r, this is theta f, and this is theta r. So this is a scenario when you have a light ray that's coming, from N1 to N2, from N1 into N2, and that's say N1 in this case, N1 is smaller than N2. So what you're going to see is that when N1 is smaller than N2, the refracted ray is actually closer to normal. We could have a situations that you have a light ray that's coming from a higher index of refraction. So let's say this is the incident light ray, and then this is the reflected light ray, and then you're going to have a refracted ray, into the second material. So this is a case when you have a light source that is in a material that has a higher index of refraction, and what you're going to see is that the light ray is actually bent away away from the normal, which means that this theta r will be larger when you compare this scenario to that scenario. This refracted ray is actually closer to a normal when a light ray is coming from the lower index of refraction to a higher index of refraction material. And when the situation is reversed, you find that the refracted ray is actually has a larger angle. Okay, so the Snell's law indicate that they are related to each other. How much light ray will be bent is actually related to the index of refraction. So we have this equation. You have the n1 sine theta 1. I'm sorry, n1 sine theta r that's equal to n2 sine theta r. So n1 of course is the index of refraction of the first material, and n2 is the index of refraction of the second material. Okay. So, and then so from this, you will be able to find out what is the angle of theta r if the other quantities are known. So an interesting phenomena actually would occur when you have a light ray that is actually in the material that has a higher index of refraction. What's going to happen is that at certain angle, after certain angle, the refracted ray will disappear. And that angle, when the refracted ray disappear, is called the critical angle. Okay, and what happened is that all the ray will become the reflected ray. So this is called the total internal reflection. Is being used in the fiber optics a lot, like cables and things like that. Okay, so so this is called the total internal reflection. Is when the refracted ray disappear, and this angle, which we call a critical angle, is when that happened. And when the incident angle is greater than the critical angle, then we'll find that only reflection ray will remain. There's no refracted ray. Okay, so this is a diagram that shows that. So you have a light source. So again, we're going to assume that N2 here is greater than n1. So a light source is in a material that has a high index of refraction. So we have the incident light ray, and this is normal as a reference. So this is your theta, which we will call our theta I, angle of incidence. And then you'll find that, at a certain point, what you can adjust the angle of incidence. So when the angle of incidence is equal to the critical angle, we found that the reflected ray is actually going to propagate along the interface. So when this angle is at 90, so this is actually angle refraction. When angle refraction is equal to 90, this is when this is when the total reflection occur, and you can actually find out what is your theta C, because by applying Snell's law, when theta I is equal to theta C, theta R is equal to 90 degrees. By Snell's law, now it tells you that sine theta C is equal to n1 over n2. So as long as we know the ratio of n1 to n2, we'll be able to figure out what is the angle, the critical angle. Okay, and any angle of incidence that's greater than the critical angle will have the will have only reflected ray. There's no more refracted ray. Okay, so that's basically a phenomena of the total internal reflection. So in this experiment, you're given this D lens, and this D lens, of course, has an index of refraction that's different from the air. Air has an index of refraction 1, and what you're going to what we'll be doing is that we're going to insert a ray onto this D lens, and we're going to study the refracted ray. We're going to measure the refracted angle, and to see if they follow Snell's law. So so you will have so you'll be like this. So this is a scenario when you have the planar surface facing the light source. So you're going to adjust the angle of incidence, and then you're going to measure the angle of refraction, and then you're just going to go by according to the numbers in the table, which I'm going to show later. Okay, and then so this is the case that is equivalent to from air to from the light ray that's in the lower index of refraction to a medium that has a higher index of refraction. And we're going to turn around after you finish this, and then we're going to turn this D lens around so that you have a light ray that's coming through the D lens first. And so the refraction will occur at this interface. So this is equivalent to when you have a light source that's in the higher index of refraction to a medium that has a lower index of refraction. Okay, so in this case, we would expect that critical angle can be found, and we would expect that the total internal reflection will occur in this instance. So based on this, this two exercise, you will be able to figure out the index of refraction of this D lens. So that's our goal. So let me just scroll down to let you see the data table. So we're going to organize the table like this. You have the angle of incidence start from 0 all the way to 80 degrees in 10 degrees increment, and then you're going to have you're going to do the scenario when you have the light ray that's in the lower index of refraction, and then for this one, this is when you have a light ray that's coming from the material that has a higher index of refraction. Okay, and then you're going to do a clockwise and counterclockwise, and then you want to find the average value, just like very similar to our lab 1. And once you have that, then you're going to plot. You're going to plot. Let me see what is it. You are going to plot the you're going to calculate sine theta I and sine theta R. Use the average value of the angle, and then you're going to plot sine theta I versus sine theta R. So in other words, you're going to plot sine theta I versus sine theta R for both scenario. Okay, and you'll find out for the planar, or for from the low to high, the slope will just give you the index refraction of the D lens. Now, for the second scenario, when you have when it's coming from the high index to low index, you'll find that the slope will give you the inverse of the index of refraction. So you can compare the value. And the index refraction of the D lens, the index refraction of the D lens is actually given, which is, let me find, okay, which is this, is 1.49, which we're going to use when you are using the tool to get your data. Okay, so basically just follow this and then get the slope, and you're going to you'll be able to find out what the M value is for the D lens. Okay, and let me see what else I want to say. So the table here, okay. And you'll find that because after certain angle for the second scenario, after certain angle, there's no more refractive ray, because the critical because when the angle is greater than the critical angle, there's no more refractive ray. So your task is to figure out at what angle is the critical angle. Okay, when the refractive ray disappear or propagating along the interface. So that is that. So you would not expect any more data after the critical angle. For example, if your critical angle is, just an example, is 60, you wouldn't expect any data point after 60 degrees because there's just no more refractive rate. Okay. Now the other thing I want to mention is that when you carry your data to the Excel, so again, you have the clockwise, counterclockwise. Make sure that when you calculate sine theta I or sine theta R, you are using the average value of the angle to calculate sine theta I and sine theta R. And don't use your calculator to process your data. You should use the Excel to process your data. Now in Excel, it does not recognize angle. So how do you convert the angle to the radian to calculate the sine theta? So this is what you want to do in Excel. You would say that on the empty cell, and then just hit equals, and then key in sine. So you have the sine, and then parentheses, and then key in pi, which is pi, and then a pair of parentheses with nothing inside. And then you multiply the angle. That's say whatever cell number that is, or you can just key in the angle. That's say angle, okay, whatever that is, and then divided by 180 degrees, and then you close the parentheses. This is how you calculate sine or cosine when you want to use Excel. First of all, you need to convert. You need to Excel does not recognize angle. It actually recognizes the radians. So you need to do this, do this sine of, and then pi, parentheses, nothing inside, multiplied by the angle, divided by 180 degrees, and then close the parentheses. Okay, so this is basically how you do the sine and then once you have the data points, then of course you'll be able to do this plotting. So you should have two plots. One is from this data set, and one is from this data set. Okay, and then let me see what else. Okay, so the data points. So again, to get a data point, you will actually get it. Let me see. Hold on. Let me bring this out first. So I will provide. So we're going to use the same. We're going to use the same. Send web tool. So this is the link you'll be provided. Again, click on the intro, and then this is exactly what we have previous for the lab one. But now you have to do something. So for the first scenario, from air to the D lens, which we're going to customize. So choose that, and we're going to use this as 1.49. That's the index refraction of the material. So, and then we're going to bring this, make sure that everything is set up correctly. Okay, I think that's a little bit off. Right. Okay, and then you're going to start from 10, right? So click click on the button, and then move this. So your task now, instead of measuring this, you are measuring this. And then it's also nice to see the intensity if you want. You can just see that a lot of light rays actually going to the second material. So again, you can enlarge this if you were able to do that. And then get a better reading. So, and then you start from, you know, clockwise, and then, so that's in this case, counterclockwise. So that's 10, and then you start from 20, okay, and you get another reading, and then 30, you get another reading, and then you go, and then after you've done so, you can see that you get, because this is from the lower index to higher index, you'll be able to find all the refracted ray. So this is a refracted ray, so you can see all the way, and then you get to like 80, okay, and you get this refracted ray, okay, and then you go, and then once you've done that, and then you just go back, you know, so that will be similar to the clockwise situation, and you take the measurement again, okay. So this is for case 1. For case 2, you are going to have the light source that's from the higher index of refraction. So we're going to change the setting here from air to customs, and then we're going to increase that to 1.49. And then this one, we're going to just use air, okay? So you can see that now the light source is at the, you know, in the material that has a high index of refraction. So we're going to go do the exactly the same thing. So you have the 10 here, do the measurements, and then at 20, 30, and you can see how the light rate changes. And then 40, and then, oh, you can see that light, you know, refractive rate disappear. So you actually have to do a little bit careful to see at what angle that this light ray disappear, maybe a little bit over, oops, all right, it just takes some adjustments, all right, yeah, so somewhere there, okay, so, and this angle will be your critical angle, okay, so we did this clockwise, so you want to do it like going back here, you know, to get the clockwise, you know, yeah, this is kind of clockwise or clockwise, you know, angle, and then find the average. So again, like as I mentioned, after the critical angle, you any angle that's greater than a critical angle, you will not see any refracted ray. So there will be no data after that. Okay, so that's basically what you want to do. Also, very simple thing to do, and so that's that.